Alright, so today we're going to be working through number 11 on the worksheet. So we're given two lines, and part A asks if the lines intersect. So the first step we need to take is we're given both of these lines in symmetric form. So to make them easier to work with, we're actually going to convert them to parametric form. So basically what this form means is that each variable is equal to t. So that's what we're going to do. So on that left equation, setting x over 2 equal to t gives us x equals 2t. Setting y plus 1 equal to t gives us t minus 1, and so on. And then we're going to do the same thing for the next equation on the right. But one thing to take notice of here is that we're setting them equal to r and not t, because all the parameter means in the case of a line is however far you're expanding that vector in order to get to any spot on the line. But these are two separate lines, meaning that the distance that they'll be extended or contracted is going to be different. So you have to have different parameters. So now that we have both of these equations set up for the respective parameters, the next step is going to be to set them equal to each other. And the reason for this is because although, to find a point where they intersect, the values of the lines need to be equal. But the main reason you can't just set them equal to each other originally, just set the x over 2 equal to x plus 4, is that they both have different parameters. So you're just going to set up an equation that has both parameters in it. And now what we've come to is an equation with two unknowns, and there's three total equations, so we're just going to set that up into an augmented matrix. So here is the augmented matrix for this situation. And so we're going to reduce to row echelon form to try and find the solutions for both T and R. So we're going to switch row 1 and row 2, and we're also going to multiply the new row 1, the one with the 1 starting, by -3 and adding it down. And as we see, you're going to get 0, -7, -7 for R. So R would be 1, but let's just say that I want to solve and put it in reduced row echelon form to solve for T1 simultaneously. So the next step would be to get a 0, and that's in that second row, but doing so gives us 0, -3, -6 in the second row, which we know is a contradiction because that would mean that R equals 2. Well, we already solved that it equals 1. So what this is telling us is that there's no solution. And if there's no solution, that means the lines don't intersect. So that's the answer to part A. Part B says, if yes, find the point of intersection. If no, find the distance between them. So we know that they don't intersect, so we have to find the distance between them. So here is this a diagram. It's a little hard to visualize, but imagine this top line going over the line on the bottom. Like imagine they're at different heights, so this one on the top just completely goes over the bottom one and they don't intersect. And so what do we need to find a distance? One of the main things is when we're working with planes, we're usually given the normal vector, but in this situation there is no normal vector. And by definition, that's a vector that is perpendicular. And so if we have two lines here, two lines which can be represented as vectors, how do we find something that's perpendicular between two vectors? We take the cross product. So to get that normal, we're going to take a cross product. So right here, we're just going to find the determinant of this 3 by 3 with the unit vectors in the top row. And so just by doing cofactor expansion, you're going to get 7i plus 1j minus 5k. So now we have our normal vector. And so what else do we need? We're going to need a point on each of the two lines to get another vector. So just by plugging in to get 0 in both the lines, you just plug that in, and so for the first equation you're going to get 0, -1, 1. Plugging that in gives you 0. It doesn't matter what you choose; it just has to be 2 points on the line. But I just picked 0 because that's the easiest. And then for the second equation, you're going to get -4, 1, 0 as another point, and plugging that in also gives you 0. And so let's subtract these points from each other to get another vector that's going to give another distance between the two lines. But remember that we're looking for the shortest distance, so this vector is not the answer. But subtracting gives you 4, -2, 1. And now we have another vector and a normal. So going back to the things we did with like the distance between planes, the easiest way to get this distance is just going to be to do a projection. So let's denote this normal vector as n, and let's call that vector, the diagonal one we created, AB. So we're going to look for the projection of AB onto n. And following the formula, we're just going to dot AB with n and put that over the magnitude of n. So as you can see, you do 4 times 7 plus negative 2 times 1 plus 1 times negative 5, which is a, b, and n dotted together. And then you just put that over the magnitude of n, and that gives you 21 over root 75. And plugging that into a calculator, you get 2.425, which is the answer we were looking for. And with that, we found the distance between the two planes.